I'm going to start recording. So here we are, next to last week. We've got our exam next Wednesday. So what I want to do is just go to our course and share some things. In fact, let me do this. Let me stop sharing for a second, and I'm going to stop my video, and that is fine. If you don't want to share your video, Brianna, that's okay. I won't get too upset. If you want to share it, you go right ahead. It's up to you. All right, so you're all seeing my screen, hopefully. Somebody.
Yes.
Okay,
Yeah.
thank you. All right, that's great. All right, so here's the deal. You've got a lot to do. This is Wednesday's homework, which I posted yesterday. My goal tonight is to go through sections 4.3, 5.2, 6.2, 6.3, and 6.5. I need to do a lot. What that leaves us for you starting, well, hopefully starting yesterday or even early today, is section 6.6, which is pretty challenging. And then we've got two sections, 7.1 and 7.2. I think I've done a really good job in doing section 6.6. I actually have a document camera where I walk. I actually do all the problems. What happens with section 6.6? It's called continuity correction, where you've got to subtract 5/10 and add 5/10. It's challenging. It can be done. It's not undoable, but it's challenging. But I've got a lot of videos, and here again, there's another document camera where I go through the problems. What I've added, because it's 6.6 you're doing, and then you're actually going into section 7.1. What I added last night is the practice video. The voiceover to the practice 7.1 section. So I actually have this in next Monday's assignment, and the directions say watch it if you need to. So it's a lot to do. Now, let's talk about our exams. Exam number 2. As was the case in exam number 1, all right, your exam will open up next Wednesday at 11 o'clock, 8/11, and close at 11 o'clock on the following day, the Thursday. I'm giving you 165 minutes. I'm giving you 15 minutes more than I gave you for the first test. Reason being, there are 5 extra questions. It's a total of 40 questions in this second exam, as opposed to 35 in the first exam. Very similar to the first exam, the questions are presented one at a time, and for security measures, once you answer a question, you can't go back to any previous question. 165 minutes is 15 minutes shy of 3 hours. In the first exam, very few people took the entire 2.5 hours. Some people did, and whatever, but whatever, you got pretty much almost 3 hours to do this. Once again, you don't spend an inordinate amount of time on one question. You just can't do that. And the reason I have it is just for security reasons. You can't go back. Once all the exams have been completed, then you can be able to see your grades. We'll talk about that. But here's the big deal as far as the exam. Our exam is next Wednesday. Well, gee, we normally have a Zoom meeting on Wednesday. Well, that doesn't make much sense. All right. Since at 7 o'clock, you'll have 5 or 6 or 10 people who have already taken the exam. So here's the deal. I will email this out to you over the weekend. We're going to hold our Zoom meeting the day before, the Tuesday. All right. And what I'll do is I'll go through sections 6.6, 7.1, 7.2, and then I'll have time to answer any questions that you may have. Speaking of answering questions, if you're planning on joining my office hour on Friday, please have questions ready. Nothing worse than you get on, I think it's 6.6, 6.5, maybe it's 4.3. Please have your questions right there and ready. Let's make the best use of the time. All right. Nothing worse when you don't know where the section is and what it is. And we just kind of, basically waste time that we don't have, basically. All right. Something else I want to share. If I go back here, and should we go back one more? Is this right here? This is super, super important. It says worksheet solutions for exam 2. Now you have these, all right, throughout the course, but what I've done is to put them in one spot. I emailed you, I think it was even yesterday, could have been the day before. Who's ever got that mic on, would you please mute yourself? What I've done is to update these. These are modified PowerPoints, right? These are the ones I'm going to share tonight. Now, in fact, as late as about an hour ago, I updated this 5.2 and I updated the 6.2, 6.3, and 6.5. So it wouldn't be a bad idea to download these. These are exactly the ones I'm going to talk about tonight. Like I say, I changed these. I've updated these last two to add a few extra things. So this is current as of about a half an hour ago. But more importantly, I got the answers to section 4.3. When I say answers, they're not just the answers, but you see that actually I have the screenshots of how the problem was done. All right. So my suggestion is, have these by your side, because I've said this before. I've said this several times. The exam will be the same types of questions. They'll be in the same order. 4.3 will be first, followed by 5.2 and so forth. What's changed is obviously the numbers that you're working with. So to have these by your side, it'd be a big plus. We're going to be talking about positive and negative z-scores. Great. I mean, you really have to have this by your side, these positives and negatives. Critical values, we'll be talking about critical values when we get to section 7.1. All right. And here again, within the PowerPoint that you'll be watching, you may have watched it already, it says, hey, print this slide for your notes. Super, super important. You're going to need these. And nothing worse than not being prepared, and you got to spend time to go looking for this, basically time that you really don't have, you just don't want to waste. What else do I have here? All right. I got critical values, and then in section 7.2, our very last section, you're going to need what's called a student distribution. There are problems where I ask you for the error, and you need to calculate that by finding the correct t-score. But I walk you through all of this. So these are all the things that you really should have by your side. So here again, I put them in one spot where you can download them and hopefully either print them out. Worst case scenario, you get them on your computer. I'm not sure how much ink you get in your computer. If you have a printer, number one, or you don't want to waste the ink or the paper, at least have them downloaded, ready to go. I mean, it takes you probably a good half an hour just to get prepared. Once you decide what time you're going to take the exam, from 11 Wednesday to 11 Thursday, have all of this before you even log on. Nothing worse than logging on and realizing, hey, I don't have what I need. Okay, so that being said, let me stop sharing this. And let me just start off with, make sure that I'm still, let me close this out for a second. I still am recording, so that's great. Let me get rid of this. And I want to share my 4.3. Like I say, these are modified. I'm not going through the entire PowerPoint that you first saw when you logged on to the homework dealing with section 4.3. I've highlighted the most important things, all right? And I've condensed this. All right, 4.3, trees and counting techniques, basically called counting formulas. There's three things we're going to encounter in section 4.3. Permutations, factorial rule number one. When you've got 8 items, how many ways can I arrange all 8 items? Factorial rule. We've got something called permutations, and we've got something called combinations. So right now, let me just do this. Let me stop sharing this screen, and let me share. Hopefully I've got this up and running. What I want to share is my calculator. And I don't have it. Let me just fire it up. Okay, there it is right here. Here you go. Share my screen. All right, first thing is the permutation. Where do I find permutation? The first slide says 8 factorial. 8 factorial implies, hey, How do I find 8 times, 7 times, 6 times, 5 times, 4 times, 3 times, 2 times 1? Yeah, I can do it on my calculator manually, but there's a key. All right, let me clear this off. It's called the factorial rule. I got 8 items. In fact, the one in the PowerPoint says, hey, I got 8 books. How many ways can I arrange 8 books? Well, any one of the 8 books can be first. After that, after I pick the first book, I've got 7 choices for the second book. After I pick that one, I've only got 6 left, followed by 5, followed by 4 times 3, times 2, times 1. It's called the multiplication rule. All right, 8 factorial. I press the 8. I go to the math key. The math key is the third thing down the left-hand side. And now I want to arrow over to PRB, short for probability. Okay, and I'm looking for the factorial. There I see it, number 4. I can press 4 or simply arrow down. Press enter, it puts a little exclamation point there. But now I have to have a calculator perform that operation. I press the enter key, and there it is, 40,320, factorial rule. If I have all the items and I need to arrange all of them, how many ways can I arrange all of them? I use the factorial rule. Second one is permutation, all right? I've got 8 items, but I'm only gonna arrange 5 of them. I've got 8 items, but I'm only arranging 5 of them. Notice I said arrange. All right. Whenever you have a permutation, the word arrangement will be stated. If you don't see the word arrangement, it's not a permutation. 8 things taken 5 at a time. It's a little different. I press the 8 things taken 5 at a time. Press the 8. I go to my math key. I arrow over the probability. I come down to number 2, permutations. I know it's permutation because I see the P. I press it, now it's waiting for the second number. I'm taking 8 things, but arranging them 5 at a time. 8 things arranged 5 at a time. And then I press enter, there it is, 6,220. Well, sometimes order makes a difference. ABC and BAC are different arrangements. But sometimes the order doesn't make a difference. It's like in a lottery. All right, lotteries are always combinations. How do I take 10 things and arrange 3 of them at a time? I press the 10. All right, I said the word arrangement, but I'm actually talking about a combination. I press the 10. I go to my math key. I arrow over to probability. I come down now to combinations. 10 things taken 3 at a time. Press the 3. Hit enter. There it is, 120. So there they all are. Permutations, combinations. I'm sorry, factorial, permutations, and combinations. Once again, when you see this on the exam, if you have to use the permutation rule, it will say the word arrangement. And what gets me is the next couple of problems will deal with combinations. Order doesn't make a bit of difference. But what kills me is I actually say how many combinations are there. And I see people using permutation, but the word combination was in the word problem. And yet you still don't even look at that. You use permutation. That one, it bewilders me. I'm kind of perplexed by that. Permutations will always have the word arrangements. If it's a combination, chances are pretty much it's going to say the word combinations, like lotteries. Lotteries are combinations. All right. When outcomes are equally likely, we compute the probability of an event by using the formula, hey, favorable over total. It's 30 women and 39 men. What's the probability you pick a woman? Well, it's favorable 30 out of a total of 69. Great. In problems we've done in the previous section, this task has not been difficult. The numbers have been small, or I gave them to you. For instance, deck of cards had 52 total cards in a deck. You had a die. It had 6 numbers on a die. Or if you had a pair of die, there were 36. Going back, the denominator, the number of outcomes was very simply, it was given to you or was fairly straightforward. The tools in this section will help you count the number of possible outcomes, the denominator, in larger sample sets of those formed by more complicated events. When the outcomes of an experiment is composed of a series of events, we use the multiplication rule to find the total number of outcomes. All right, here's an example. Jacqueline is in a nursing program, and she's required to take a course in psychology, anatomy, and physiology, and she's also taking Spanish too. There are 2 sections in psychology, 2 in A&P and 3 in Spanish. How many different class schedules can Jacqueline choose from? Well, To explain this, I use a little diagram here, a little tree diagram. Here's Jacqueline here.
Excuse me, I don't think you're sharing your screen.
You seeing it now?
Yeah, now.
It wasn't being shared before? Okay, yeah, because I had the calculator on. Thank you. Who was that?
Brianna.
Brianna, thank you, because everybody else is sleeping apparently. Thank you, Brianna.
Welcome.
All right, here's Jacqueline over here. She has two choices for psychology. Let's say she chooses this one on Mondays and Wednesdays. Now she's got two choices for A and P. Let's say she chooses that one. Now she's got three choices for which Spanish class she gets. Well, the end result, the end here, it has three different branches, three different ways. And then this one has three, this one has three, and this one has three. You can see there are 12 ending branches. All right, Jacqueline's got one of 12 different course schedules she can take. Well, instead of drawing two tree diagrams, an easier way to do it is use the multiplication rule. She had two choices for psychology, two for A and P, and three for Spanish too. She had 12 choices, a lot easier than doing the tree diagram. Now, this is not the permutation rule because we're not arranging 8 things at a time. This is just telling me, hey, how many different class schedules? The idea is the multiplication rule does it for us. An identity theft. Someone says, oh, I just happened to guess your social security number. Well, your social security number has 10 digits on it. Any number from 0 to 9 can be the first digit. Any number from 0 to 9 can be the second, all the way out to 9. If you multiply this, there's 1 billion different social security numbers. So somebody happened to guess it. They're probably somehow just guessing your social would be 1 in a billion. No, they didn't guess it. They did dumpster diving. They went into your garbage and they found your number on a bill or something. All right. Multiplication rule. All right, we talked about factorial. How many ways can 8 books be arranged on a shelf? We have 8 books for the first, you have 8 choices for the first book. After you choose the first book, you have 7 for the second book, and then you have 6 and 5. Easy enough to do, but the fact is the calculator makes it a lot easier by using the factorial. 8 factorial, we found out, I started out, I had an answer of 40,320. You press the 8, you go to the math key, you arrow over the probability, you come down to the exclamation point, which is factorial. Just for general knowledge, 0 factorial is 1 and 1 factorial is 1. N factorial means n times 1 less than n times 2 less than n, and so forth. 4 factorial, 4 times 3 times 2 times 1. Your calculator could do that for you. During the summer, you plan on visiting 6 national parks. You're going to Glacier, Yellowstone, Yosemite, and so forth. You would like to plan the most efficient route to decide. You'd like to plan the most efficient route, and you decide to list all the possible routes. How many different routes are possible? Well, there are 6 factorial. After you pick the first national park, there's 6 choices. After you pick the first, you got 5 for the second park you're going to visit, and then 4 for the third park, and then 3 for the next park. All right. So 6 times 5 times 4 times 3 times 20, or just using the calculator to put in 6 factorial, there are 720 possible routes. But don't forget, now we're finding out these denominators, but I still may ask you a question like this. Hey, what's the probability that you pick the shortest route? Well, it'd be favorable over total. Well, we know the total is 720. There's only one shortest route. What's the probability of just by chance picking the shortest route? It'd be 1 chance over 720. So even though we're doing counting here, don't forget the course is still deals a lot with probability. 1 over the total. What we're focusing on is this total, all right? Because we haven't encountered this. We were working with decks of cards, or if a woman had a child, there were 2 choices, male or female. It was pretty obvious. This one here wouldn't be obvious unless you knew something about factorial. All right. We've considered the number of ways of arranging 8 books on the shelf. It was 8 factorial. But suppose you only have room for 3 books. All right. I could go 8 times 7 times 6. I got 8 choices for the first book. I have 7 choices for the second book and 6 choices for the third book. Multiplication rule. There are 336 possible arrangements. If I have 8 books, how many ways can I arrange 3 of them? 336 ways. Wow. The formula we can use to compute this, however, instead of using the multiplication rule, is called the permutation formula. Now, I give you the formula, but I also give you the calculator way of doing it. All right. My advice to you is you're never going to use the formula. You're going to rely on the calculator. Notice there's that word arrange. When I see the word arrange, I know that order counts. Order makes a big difference. It's like A, B, C is different arrangement than B, C, A. Different arrangements, they all count. I know I'm using the permutation rule. I've got 8 things and I'm arranging 3 of them. And the answer is exactly what you saw with the multiplication rule. You could rely on this, but I think in most cases, it's just easier to use the calculator. 8 things taken 3 at a time. Order is important, and you'll know that because you'll see the word arrangement. All right, let's compute. All right, you got 5 chairs. You got 8 people, but you got only 5 chairs. All right. List the number of possible seating arrangements. You get 8 things taken 5 at a time. Well, granted, I got 5 chairs. I can put any one of my 8 people in the first chair. Then I got 7 people that can sit in the second chair, and 6 in the third, and 5 in the fourth, and 4. I could use the multiplication rule, but I find it easier just to use the calculator and use 8 things taken 5 at a time using the permutation app in the computer. I'm not going to use the formula. In fact, I actually show you what the formula is here. It's n factorial divided by n minus I. I don't want to even spend any time on that. There is no need of using the formula, but I don't want to cheapen the course out and say, well, you can't do it. But if we were in class, I would talk a lot about the formula, but still the best way of doing it is using the multiplication rule if you can handle it, or simply use the calculator, the permutation function. 8 things taken 5 at a time. Notice the word arrangements. I know it's a permutation. That order makes a difference. There's the answer. All 3 ways of doing it: formula, multiplication rule, and using the calculator function. 3 offices: president, vice president, treasurer, must be selected from among these 12 people that are on the board of directors. All right. How many different slates are possible? We will review a slate of offices as a list of 3 people, with the president listed first, the vice president second, and the treasurer third. For instance, if Mr. Acosta, Ms. Hill, and Ms. Smith wish to be on the slate together, there are several different slates possible depending on which person is listed for which office. All right, is Mr. Acosta running for president, or is it Mr. Smith, or is it Ms. Hill? Order makes a big difference, because if I put Mr. Smith first, he's running for president. If I put Ms. Hill first, she's running for president. And the same thing applies for vice president. Order makes a difference. So if there's 12 people, I have any one of the 12 people could run for president, and then I got 11 people who could run for vice president, and 10 people who could run for treasurer, 1,320. I could have done this with the formula. I would suggest simply using the calculator function to do that. Order makes a big difference, because the slate has always the president first, the vice president second, and the treasurer third. If I rearrange that, then I've got a whole different slate of people running for office. Permutation, order makes a difference. With a requirement you have of a permutation, you have n different items available. You're selecting R of them. We consider rearrangements of the same item to be different sequences. Order makes a difference. The permutation of ABC is different from CBA, and it's counted separately. Order makes a difference. In each of the previous counting formulas, we've taken order of the objects into account. However, all right, so let's say you have a class in political science. In fact, it doesn't have to be political science. It could be anything. When you were in high school, all right, maybe your English teacher gave you a reading list for the summer. All right, she gave you a list of 10 books, or he gave you a list of 10 books, and you needed to select 4 of these books, either to read during the summer or maybe even read through the semester. The order in which you read the books was not important. It was up to you. You had 10 books to choose from. All right, you're gonna read 4 of them. The order in which you read them doesn't make a bit of difference. All right. So what we're looking for now is different groupings, or simply we're looking for different combinations. Order doesn't make a bit of difference which book you read first. All right, there's a formula for combinations. It's n factorial divided by r factorial divided. Hey, don't worry about that. All right, in fact, r and x are one and the same. I give it to you because it's part of the course, but you're not going to use it. There's a calculator function. In your political science class, you're assigned to read any 4 books from a list of 10. How many different combinations or groups? When you see word combination, guess what you're using? The combination function in the calculator. In this case, we're interested in combinations rather than permutations. 10 books taken 4 at a time. Here's the formula. Why use that formula when you can do it real easy with your calculator? You put the 10 in first. You go to the math function, you arrow over the probability, come down to combinations. You hit enter, you press the 4 and then hit enter again. And I'm pretty sure I did at least one video somewhere dating back to either last Monday, or I know I did videos on this. All right, difference between combinations and permutations and how you access them on your calculator. And there it is there. You would enter the 10 first. You would go to the math key. You would arrow over to probability, PRB. You would choose combinations, hit enter, and then you would press the number 4 and hit enter again, and it would give you 210. No need of using the formula. All right. How many 5-person committees are possible from a class of 20 students? Well, if you're on a committee, no one's any more important than the other. In other words, there's no president, vice president, and treasurer on a committee. Order doesn't make a bit of difference. You're just part of a committee. No one's any more important. There's no president here again, vice president, and so forth. It's a combination. 20 things taken 5 at a time. 15,504. There'll always be less combinations than permutations. Please, if you see a problem on the exam that deals with a lottery, lotteries are combinations. Well, the first thing, if you ever bought a lottery ticket, like a Mega Bucks ticket, or any game, Powerball, Mega Millions, when they print the numbers out, they print them from smallest to largest. All right, they always do that, from smallest to largest. But when the numbers come out on TV, they don't come out in order. They come out in a random order. It's hard enough to win the lottery as it is, let alone to get them. They would have to come out from smallest to largest. I've never seen that happen. All right, here's this. If you clicked on this back in July, whenever I recorded this, the numbers came out 35, 18, 23, 32, 29, 25, and 12. Here's what my ticket said. All right, I won because order didn't make a difference. Look at the probability. To win the lottery with 6 numbers, you have a 1 in 13 million chance, almost 14 million. If order did make a difference, if they had to come out in order, it'd be 1 in 10 billion. Folks, no one's going to win that lottery, 1 in 10 billion. It's tough enough to win the lottery at the Mega Bucks as it is. Order doesn't make a difference. So once again, please don't throw points away. If you have a problem on the exam, guess what? You will. And it'll be a lottery. A lottery is always a combination. In fact, many of the problems I do, I said, well, give me how many combinations. And I can't get it through my head why people use the permutation instead of the combinations. Lotteries are combinations. The tickets are printed out from smallest to largest, but when they draw the numbers, they don't come out that way. I've never seen. It'd be interesting to call the lottery and say, hey, if you ever pulled 6 numbers out and they came out numerically from smallest to largest, I doubt that's ever happened. 1 in 10 billion chance. My gosh, you can't win now with 1 in 13 million, let alone 1 in 10 billion. All right, so that's 4-3. Give me a second here while I call up my stuff. That was 4-3. Now I want to do 5-2. And there was only one section that we did in chapter 5, and that was 5-2. We didn't do 5-1, nor did we do 5-3. Seeing my screen, hopefully. I don't want to move on.
Yes.
You still see me recording?
Yes.
Yes.
Okay, great. Thank you. I appreciate that. I'm good, but I'm not perfect. There's only one person who walked the earth that was perfect. And it sure as heck isn't me. And guess what? It's not you either. Binomial probabilities. The central problem of binomial experiments is finding the probability of R successes out of N trials. Now we'll see how to find these. Give me 1 second here. I just want to check the time. All right, half an hour. Okay, good. I'm on track here, I think. I don't want to rush through this, but I got a lot to get through. I don't want to belabor the point and bore you. Very important. Here again, I say this stuff. Maybe I would say have this slide, this slide printed out. All right. In fact, in the PowerPoint, I actually tell you to do that. You know, thing is, you get an expression, but you got to kind of translate that expression to a inequality. 4 or more, at least 4, no fewer than 4, no less than 4. What does that imply? R is 4, 5, 6, and so on. 4 or fewer, at most 4, no more than 4. The number of sequences does not exceed 4. Well, R is less than or equal to 4, which means that R could be 0, 1, 2, 3, or 4. More than 4, the number of successes exceeds 4. Well, R is greater than 4, which means R could be 5, 6, 7, and so forth. Fewer than 4, the number of successes is not as large as 4. It means R is less than 4. Well, less than 4 would be 0, 1, 2, or 3. All right. This problem is typical of an entire class of problems that are characterized by the feature that are exactly 2 possible outcomes for each trial of interest. These problems are called binomial experiments after this guy, Jacob Bernoulli. All right. Here's what you're going to, one of these 5 things is going to happen. All right. One of these 5 situations are going to occur. You've got 2 different calculator functions. One is called the Binomial Pdf, and the other one is called the Binomial CDF. If I ask you, find a probability of exactly 4 successes out of 7 items, you're going to use the PDF, okay? What if I said, hey, 4 or fewer, or at most 4, no more than 4? Well, that would imply I'm looking for the answer of 0 successes with 1 success added with 2 successes added with 3 added with 4. The reason I say added, it could be 1 success, or it could be, 0 successes, or 1 or 2. But we know back in section 5, back in probability, going back to, I believe it was section 4.2, we know that the ors means we're adding probabilities. What the cumulative is going to do, it's going to take the probability of 0 successes, add it with 1, add it with 2, probability of 2 successes, add it with the probability of 3, add it with 4. It does all of this work for you. It starts at 0. It always starts at 0, and it stops where you tell it to stop. You're using CDF. Another way you'd be using CDF, let's say I said 4 or fewer than 4, or the number of successes is not as large as 4. Well, what does it mean, fewer than 4? Fewer than 4 means 0, 1, 2, and 3. I want the calculator to add up all of these probabilities in one step. I'm using CDF. These are what I call the front end, both of these, the front end. Sometimes I'm looking for the back end. Well, I could find a probability of 4 and then add it to the probability of exactly 5 and add it to the probability of exactly 6, or add it to the probability of exactly 7 by using the PDF. No, I don't want to do that. It'd take me too long. What I want the calculator to do is use CDF, find a probability of 0 or 1 or 2 or 3, but that's not what I'm looking for. I'm looking for the back end. But I know the probability of these things happening plus the probability of those 4 things happening equals 1. So I use the complement rule. When you're finding the back end, you've always got to take 1 minus using the binomial CDF. And the same thing happens with this last one here. Whenever you're finding the back end, all right, You're going to find the answer here, because I know that the answer for this part plus the answer for the last part, the back end, has to equal 1. So if I take 1 and I subtract this answer, I get what I'm looking for. Another important slide maybe to print out, all right? Only one time you use the PDF when you want to find exactly a value. If you're finding the front end multiples or the back end multiples, you're going to use CDF. It's just that here on the back end, you're going to have to subtract from 1. The complement rule. Privacy is a concern for many users of the internet. One survey showed that 59% of internet users are somewhat concerned about the confidentiality of their email. Based on this information, what's the probability that for a random sample of 10 internet users, exactly six are concerned with their privacy? Exactly 6, it's the PDF. All right. Binomial experiment, there's 10 trials. If we assign success to being an internet user at 59%, we are interested in a probability of exactly 6 successes. What I'm doing here is spelling everything out. There's a formula for this. There's always a formula for everything in mathematics, but the calculator does all the heavy lifting for you. You're never going to have to use this formula, but I don't want to cheapen the course out by saying that you're not smart enough to figure this out. Yeah, you're bright enough. It's just that you don't have to use it. All right, there's a formula for it. And it's kind of not complicated, but it just takes time. And I'm not even going to spend a lot of time explaining how the formula was developed. It's just there. Doing it with a formula, we come up with 0.25, which says, hey, there's a 25% chance that exactly 6 people are concerned about their privacy. But there's a calculator function that does the formula for us. He says, go to Binomial Pdf, second function of VAR's menu, and you arrow down to Binomial Pdf. All right, so there's that same problem done with a formula. All right, here I am using my calculator. I went to second function VARs. I arrowed down to Binomial Pdf. How many trials are there? And it's 10. What's the probability of a success? It's 59%. Please, ladies and gentlemen, don't put the number 59. 59% is 0.59. You know your probabilities have to range between 0 and 1. They can't be negative and they can't be bigger than 1. It sure as heck ain't going to be 59. 59% is 0.59. If you're getting some crazy answer because you probably didn't change that percent into a decimal. All right, we're looking for exactly 6. I press paste. I go down at paste. I hit enter. And there's my answer, 0.250, which is the same as 0.25. I just have an extra decimal place. The calculator does it for you. You don't have to use the formula. PDF, exactly 6. All right, now what he says here is that, yeah, you can use the PDF, all right, but for cumulative probabilities, you use the one that's below PDF, which is called CDF. The C stands for cumulative. All right, 45% of adults questioned report that their health was excellent. The researcher wishes to study the health of people living close to a nuclear plant. Among 11 adults, there's my end value, randomly selected, only 3 reported that the health was excellent. Find a probability that when 11 adults are randomly selected, 3 or fewer. So what I did is I wrote down the numbers from 0 to 11. All right. I could have 0 successes, have 0 people of excellent health, 1 person, 2 people, whatever. Problem says, what's the probability of 3 or fewer? Well, 3 or fewer includes 3, includes 2, includes 1, and includes 0. These are all numbers that are 3 or fewer. Obviously, 4 is not 3 or fewer. So I go to Binomial CDF, second function VARs, arrow down to Binomial CDF. What the calculator is going to do for us very nicely, it's going to take the probability of 0 people having good health, add it to the probability of 1 person having good health, add it with the probability of 2 people having good health and adding it to the probability. It's going to do all of this for us in one step. All right, cumulative. It saves us the time of doing PDF 4 different times. And there's the answer, 0.191. Now notice the answer here is spot on. I'll talk about things that aren't going to be spot on as we get to those slides. CDF, front end. what's the probability that at least 4 seeds will germinate? Well, what he's telling us here is that he knew the answer for 4 seeds germinating. He actually went out and he found a PDF of 5 seeds germinating, and then he found the probability of 6 seeds germinating. Well, why do that? You know, it takes you time to find those 3 answers, then you got to add all those 3 answers together. He gets an answer of 0.745. So what I've done here is I've done it, you know, with the calculator. What's the probability of more than 4 seeds germinating? All right, so I'm going, it's the back end. I'm looking for either 4 or 5 or 6. I'm looking for this answer, the sum of these. I'm going to use CDF, but the CDF does not start where you tell it to start. I can say, hey, Mr. Calculator, start with 4, add the probability of 5, and then add the probability of 6. The CDF function always starts at 0. So what I'm going to do, I'm sorry?
Sorry, wrong first. Sorry.
Please mute yourself. What I'm going to do is find this front end. I'm going to use the cumulative and stop right here. Notice the 3. When I say here, I got 6 trials, the probability of something germinating is 0.7 or 70%. I'm going to stop at 3. Once I know this answer, I'm going to take this answer and subtract it from 1, and that will give me what I'm looking for, the back end. Whenever you're looking for the back end, you're going to have to use the complement rule. And notice where I stop right here, because I'm looking for greater than or equal to 4. I'm looking for the probability of 4 added with 5 added with 6. Yeah, I could have done it PDF 3 different times and added those answers, but why? Use the CDF, find the front end, find this right here. And then, but see, when you know you're finding the back end, what you got to really do, remember, is you got to put the 1 first and then put the subtract sign and then put the binomial CDF. Notice where I'm stopping. I'm stopping at 3. Once I know this and I take that answer and subtract it from 1, I get the back end. In a certain college, 33% of the physics majors belong to ethnic minorities. The 10 students are randomly selected from the physics majors. What's the probability that no more than 6? Well, what's no more than 6? 0 is good, 1's good, 2 is good, 3, 4, 5, 6 is good, but no more than 6. Hey, it's CDF. Notice I'm looking for the front end. No need of doing any subtraction because CDF always starts at 0. Well, that's great. It's where I want to start. And I want to stop at 6. There it is. I got 10 trials. Once again, 33% is not 33, it's 0.33. And I'm telling it where to stop. When I say 6, he starts at 0, takes the answer for 0, adds it with 1, 2, 3, 4, 5, and then finally he finds the answer for 6 and he stops and adds those all together. It's the front end, easy beans, CDF. Now it's a little bit of discrepancy, 0.981, the correct answer is point, but no, it's nothing even kind of close to this. I mean, well, I take that back. Here's what I'll do. I'll make sure, all right, I don't want to play games with this, all right. The only way you would get the exact answer if you use the formula. I don't want you to do that. But here's what I'll do. I'll go through before the test is published. I'll go through and I'll make sure an answer like letter A is, even though 982 is closer to 981 than 985, I'll make sure that there's nothing else even in the ballpark. I'm not going to be nickel diming you. All right, find a probability of at least 2 girls and 7 births. There's at least 2 girls and 7. Assume male and female births are equally likely. At least 2 means 2 or more. At least 2 in English means 2 or more. Yeah, I could use PDF. I could use it 6 times. I don't want to do that. I'm going to use CDF. All right. I'm going to use CDF because CDF always starts at 0. It stops where I tell it to stop. I want it to stop right there. Once I know this answer, I take that answer, which is right here, and I subtract that from 1. By subtracting it from 1, it gives me what I was looking for, the back end. Whenever I call it the back end because it's the back. All right. If you're ever given a back end problem, you got to be subtracting from 1. Now, people say, well, oh, I forgot to subtract from 1. Well, you could have done here. If you do just this here, You can always subtract 1 from it later on at the end. It's just that your answer is going to be negative, but the number will be the same. It's just that it'll be a negative number. So you don't have to start the whole thing over again. Back end, you're always subtracting from once. Put the 1 in first, hit the subtract key, and then the binomial CDF. It's called the complement rule. We've seen the complement rule. You know, probably if something happening is 0.7. What's the complement of 0.7? 0.3, because they add up to 1. 1 meaning something's going to happen. It's a sure thing. The last one here is something about insurance companies. You have 14 drivers. What's the probability of getting 3 or more? 3 or more means 3 all the way out to 14. Well, guess what? I don't want to use PDF 11 times. I'm going to use CDF. I want it to stop right here. That's why I'm using that value of 2. I want it to stop. Once I know this, I'll take that answer, subtract it from 1, and I'll have what I'm looking for, this back end. Once again, I'll say it again. Back end means that you're going to have to use the complement rule. So you're doing these problems. I mean, it's going to require, in this case here, there's 14 drivers. Write the numbers 1 to 14 out and say to yourself, what's it mean for 3 or more? And I just highlighted it here with my yellow marker. 3 or more means 3, 4, 5, 6, all the way to 14. Find this answer, subtract this answer from 1, and you'll get what you're looking for. 3, 4, 5, all the way out to 14. Hopefully that helps. Hopefully that helps. Oh, I keep saying that. Of course, it's going to help. Give me a second here. You all see my screen?
Yeah.
Good. Good, 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 good. All right. You may say, well, why is he combined? He's calling this 6, 2, 6, 3, and 6, 5. Why is he combined all of these into one PowerPoint? Well, the reason being is that the problems in 6, 2, and 6, 3, and 6, 5 are all done the same way. There's little discrepancies, but for the most part, they're all done the same way. All right. Why are we coming up with a new way of finding probability? This is what these sections deal with. Even in 6, 6, they all have a new way of finding probabilities. You say, well, why? What was wrong with the ways we had before? Well, here's the deal. Back when we did probability in section 4, we were dealing with things that you didn't know at the time were called discrete random variables. A woman has 7 kids. How many were boys? Well, it's either going to be 1, 2, 3, 4, 5, 6, or 7. You roll a die, you know, what's the probability that the number is a 5? Or you pick a card out of a deck. How many, what's the probability you get an ace? Those answers to those problems were all whole numbers. They were discrete. The things we're going to talk about now are called continuous random variables. We're going to talk about people's weights and people's heights, things that don't necessarily end up as a whole number. All right, those are called continuous. I'm not going to quiz you on this. I'm just laying the groundwork of why we're doing something different. And that's something different that we're going to have to do. Well, in fact, before I even get there, the number of eggs a hen lays. Well, a hen can't lay 2.341 eggs. It's going to lay 2 eggs, 3 eggs, 4 eggs. The number of statistics students in a class. Well, you can't have 1 and 3/4 students. All right, you're going to have 1, 2, 15, 20, 30. The amount of milk a cow produces. Well, a cow, chances are, isn't going to produce exactly 2 gallons of milk. It's going to be 2.136. It's going to be some decimal. It's going to be a continuous random variable. The things we deal with in chapter 6 are all continuous random variables, which means that we've got to come up with a new way of doing things. This is here again, I'm beating the dead horse. Discrete are things that are countable, right? They're whole numbers. Something that's continuous could be anything over this range here, something like a voltmeter, all right? Has the possibility of being a decimal. It doesn't have to be, but it has the possibility. A woman has 7 kids. Well, guess what? She's never gonna have a possibility of having 2.3 kids. It's gonna always be a whole number. All right, so what this all means is that you're gonna have to draw a lot of normal curves, the bell curve. There is no way on God's green earth you're going to be able to do the problems in chapter 6 if you are not drawing bell curves. Now, the great thing about this bell curve is the area underneath the curve is exactly 1. Oh, isn't that great? The sum of the probabilities of everything in the sample space has to equal 1. All right, this is how I can equate area with probability. Suspiciously, the area under this curve is 1. What I would suggest is maybe for test purposes is have some scrap paper and you've already drawn some bell curves. You haven't labeled anything under them, but you've drawn them already. I mean, how hard is it to draw a bell curve? But I would make sure you've got some scrap paper available. Once again, I'll say this. If you're not drawing the bell curves in chapter 6, there's no way on God's green earth you're going to get these right. It's not a hard thing to do. All right. So first thing, before I even get started, if I go all the way to my right on the number line, I'm going to positive infinity. If I go all the way to the left, I'm going to what's called negative infinity. Well, your calculator doesn't have any key. We go back, it doesn't have any key that says infinity. So watch what I'm going to do here. I'm going to stop sharing this. I'm going to fire up my calculator. I'm going to show you on the calculator how you designate infinity. You all see my calculator?
Yeah, now I do.
Okay, great. All right. There's no key that says infinity. All right. Sometimes you got to put in negative infinity. Sometimes you got to put in positive infinity. Where I see people having a problem is with negative infinity. Let me go to vars. Now, we go to second function, vars. We come down to normal cumulative. That's where we're going to be. We're going to be in normal cumulative and we're going to be in inverse norm. Numbers 2 and 3 are the only ones we're going to use right now. All right. I mean, before we were down the previous section, we had PDF and CDF, but now we're back at the top. All right. We never use the PDF. It's always the CDF in chapter 6 and the inverse norm in chapter 6. Let's assume that I want to put in negative infinity. Here's the mistake that people do. Instead of pressing the white key for negative, no, they press this key here. This gray key is not the negative. It's the subtract key. If I use this, if I go that key, if I hit the wrong key and I go E99, my E is right. It's the second function of my comma. Second function, I press the comma and I press 99. If I were to go through with this, in fact, let me just do something here. Put some numbers in and just come down and hit paste. That's what's going to happen. Your calculator is going to give you an error message, error with syntax. Syntax means you put in the wrong negative key. Let me quit out of this second function. Let me quit out of this, clear this out. I want to go second function, vars, come down to CDF. The way I enter in negative infinity is this way. Here is the negative key, the negative, all right? This gray one is the subtract key. They're different. Negative, I want E99. Second function, hit the comma key, and then put a 99. Sometimes your calculator will put a -1, no big deal. Now watch what happens when I hit paste. At least now I'm not getting any error message, all right? So that happens quite frequently. People use the wrong key. This is the negative key. That is the subtract key. Matter of fact, only time you would be using the subtract key if you were finding the back end of a binomial probability problem, 1 minus binomial CDF, all right? That's the only time you're using the minus key. This is the negative key. It's a big deal. Let me stop sharing that. Let me close this out and let me go back to sharing what I was. All right, so once again, you're gonna have to draw a lot of these curves, all right? We start out very easily. We start out what's called a standard normal. What's a standard normal? Suspiciously, the mean of this data set is exactly 0. And lo and behold, the standard deviation is exactly 1. All right, it's kind of, in reality, it doesn't happen, but we have to start out somewhere. We start out real small or real easy. Mean is 0, standard deviation is 1. The key thing is the area under the curve is equal to 1, which means that I can associate area with probabilities. That's the key thing. Now, we've seen this before. We were using these bar graphs. Actually, this is a histogram, all right? And here I'm overlaying a normal curve, all right, over the histogram. Now, notice we're talking about heights of females, all right? So, you know, a 3-year-old is not going to be exactly 3 feet tall. They're going to be 3 feet, 1 3/4 inches, right? So this is why I'm using this bell curve here. Suppose, all right, so we're headed that way. But before we get there, we have some things to talk about, all right? And one of those things is what's called z-scores and raw scores. Suppose Tina and Jack are on 2 different sections of the same course. Each section is quite large, and the scores on the midterms had a normal distribution. Normal distribution means there were some low scores, some middle scores, and some very high scores. In Tina's section, the average was 64. She scored a 74. In Jack's section, the average, the mean was 72, and he scored an 82. Both Tina and Jack were pleased with their scores. Each was 10 points above the average with respect to their respective section. However, the fact that each was 10 points above does not really tell us how each did with respect to the other students in their sections. To be quite honest, I'd rather be Jack than Tina. I got the 82, all right? Tina got the 74, but we're interested in how they did in respect to everybody else in their class. All right, so this is Jack's class. Notice how spread out the curve is, all right, which means the standard deviation was quite large. It was 10. Tina's section, the curve is a lot more compressed, but notice her standard deviation, her class was 5. The smaller the standard deviation, the closer the scores are to the mean. In our first exam, I think our mean score was something like 83. All right, so Jack's class and Tina's class. Now, notice the mean here in Jack's was 72. He scored an 82. Her class had a mean of 64. She scored a 74. Yeah, great. They're both with 10 points above. Doesn't tell us any much. What we want to do is to standardize this. And how we standardize this is we take the scores and we convert them to z-scores. There's a little formula. You take the raw score, you subtract the mean, and you divide it by the standard deviation. X minus mu divided by the standard deviation. It's called a z-score. What the z-score is telling me is how many standard deviations was that score above the mean? How many standard deviations? A standard score, a z-score, is a measure that tells us the number of standard deviations the measurement is from the mean. If you have a positive z-score, your measurement or your score was above the mean. If you have a negative z-score, your score was below the mean. All right, so taking Jack's class, all right, taking Jack's score of 82, subtracting the mean, which was 72 for his class, dividing it by the standard deviation, Jack's score was 1 standard deviation above the mean. Doing the same thing with Tina, she had a 74. Her mean of her class was 64. Her standard deviation was 5. Tina's score was 2 standard deviations above the mean. Tina did better in relation to everybody else in her class. She was further away from the mean, which means she had a real higher score in relation to everybody else. Her z-score was 2, Jack's z-score was only 1. Here again, in the real world, you'd rather be Jack because, you know, I mean, Tina can brag all day long, you know, she was 2 standard deviations above the mean, and Jack gonna say, well, Tina, I still scored 10 points better than you. So in the real world, you know, Jack's looking great. Tina can brag, but I still rather have an 82 than a 74. A lot of times, we want to compare measurements that have different labels. For instance, heights are measured in inches and weights are measured in pounds. And what we're looking for here is what is more extreme. Someone who his height is 76.2 inches. Let's see, 6 foot would be 72. So somebody's, 6'4" versus somebody who weighs 237 pounds. So I take both these scores, I convert them to z-scores. I take the raw score, subtract the mean, which he tells me for all men height-wise is 68.34 divided by, he tells me the standard deviation. A height of 76.2 has a z-score of 2.6. A weight of 237 only has a z-score of 2.45. So it's more extreme to be 6 foot 4 inches than it is to a man to weigh 237 pounds, which, it's kind of sad, but let's face it, we're living in a generation where, fast food and all that, and it's more extreme to be 6'4". Think about, how many people 6'4", as opposed to how many men weigh 237 pounds, slightly higher. Here's the deal. If you have something has a z-score that's bigger than 2, it's unusual. Or if you have a z-score that's less than 2, it's deemed to be unusual. So it'd be unusual to find somebody 6'4". In my own life, I maybe know 2 or 3 people that are 6'4". All right, but I know several people that are 237 pounds, z-scores. All right, so that's the background. We haven't gotten started yet, but that's the background of where we're headed with this. Standard normal. Well, guess what? Test starts out with section 4.3. Then I go to section 5.2, binomial probabilities. Back in 4.3, what are we doing? Factorial rule. We're using permutations if the word arrangement is there. Then we're using combinations if we're only arranging some items and order doesn't make a difference, like lotteries, combination. All right, then 5.2, we had binomial Pdf, CDF. Well, then what's going to be next? Standard normal. In fact, even when I label the problem at the very top of that section, I call it standard normal. Now, here's what's going to happen. The long and the short of this. We're going to be asked to find the area, which is the probability, sometimes to the left of a vertical line, sometimes to the right, and sometimes we're going to have to find the area in between. This is standard. This happens in section 6.2. It'll happen in 6.3. It'll happen in 6.5. It'll happen in 6.6. We're going to need to find the area to the left, to the right, or in between. But there are going to be slight changes in how we do that. But the fact of the matter is going to be one of those 3 situations are going to develop: left, right, or in between. It'd be a futile task to try to set up tables under the normal curve for each different combination of mu and sigma. I mean, how many different combinations could we have? Unlimited number. So he says, hey, we need a way to standardize this so I can use one table to find out anything I need to find out, whether it's people's heights, people's weights, whatever. I need a way of standardizing this. All right. And we're going to use those z-scores to achieve this, this goal. Now, we start out with a standard normal. Here's why. If I'm doing a standard normal, the z-scores are always the x-scores minus the mean divided by the standard deviation. Well, in the standard normal, the mean is 0, the standard deviation is 1. What ends up happening is my z-score and the x-score are one in the same. I don't have to do any converting. Z and X are synonymous, called a standard normal. This won't always be the case, but it's nice to get started with something easy. Z and X are one and the same. If you have an X score is equal to the mean, your Z score is going to be 0. If your X value is to the right of the mean, your Z score is going to be positive. If your Z score is left of the mean, your Z score is going to be negative. Kind of basic. It prevents you from making some silly mistakes. If I'm to the right of the mean, my Z score is positive. If I'm to the left of the mean, my Z score is a number line. Standard normal. We're going to use tables. I'm going to show you how the table is important, but not really, because the calculator will do a lot of this. It's just that what happens with the calculator and the number of decimal places we're using, sometimes there'll be discrepancies. If you want to be spot on, then you're going to have to use tables. Not many people do. They trust that calculator. And like I say, I'm not going to be nickel dime. I'm not going to put a couple of answers that are real close, but I'll show you what I mean from that. All right. our table, if you looked at the video, Al talked about a center table. Then he says, nah, we're going to be using what's called a left-handed table, not a center table. All right, here's an example of the positive z-scores. And this is an example of the negative z-scores. Yeah, I would print these out. Will you depend on these? Yeah, really no. All right, but it wouldn't be a bad idea to have it. However, when we get to section 7, chapter 7, especially those t distributions, yeah, you gotta print that table out. You definitely have to print it in chapter 7. Yes, you could do it here, but I'm going to show you how you calculate it. You know, if you haven't thought to yourself, if I rented this calculator for $20, I mean, that's the best $20 I've spent in a long, long time, the things that it does for you. Here's an example. You get the precision instrument company. You know, this is with a word problem, getting by all the gooply-guck and getting down to the crux of the problem. I mean, who really cares if it's the Precision Scientific Instrument Company? It could be called Joe Blows, you know, but read through the problem. Thermometers are supposed to give readings of 0 degrees centigrade at freezing point of water. Test on large sample of these instruments revealed that the freezing point of water, some thermometers gave readings below 0, and then some gave it above. Now we're getting down to the problem. Assume that the mean reading is 0 degrees and the standard deviation is 1. Oh, I got a standard normal. Fantastic. Also assume that the readings are normally distributed. And now he asks me the question finally. If one thermometer is randomly selected, find a probability that the freezing point of water, the reading is less than 1.27, less than. First thing I do is draw a bell curve. My mean, now the mean is right at the center, it's the highest point. In fact, when you have a standard normal, the mean and the median are one and the same. I'm calling this the mean right now. There's my 0, the highest point right in the middle. Well, if this is 0, kind of makes sense that 1.27 on the number line is to the right of 0. It's not going to be to the left. It's got to be a negative number. That's the first thing. You draw your curve, you put your 0 right in the middle, you figure out where, you know, looking for the probability at the freezing point of water, the reading is less than 1.27. Well, less than is not to the right, less than is to the left. Fantastic. I'm looking for this area right here. This area right here is going to equate to the probability that a thermometer has a reading of less than 1.27. Area under the curve equates to probability. But I got to draw my curve. I got to know what I'm looking for. Okay, fantastic. Go to my chart. All right, here again, I'm talking about this chart. I don't think you'll have to do it, but I got to show it to you anyways. Where do I find 1.27? Left-hand column, I find 1.2. I add 0.07 to it. I get 1.27. Now, where this vertical line and this horizontal line intersect, there's my area, 0.8980. Not so bad. You know, I have to pull my table up and doing it. Okay, not so bad. Here it is. It says the probability of randomly selecting a thermometer with a reading less than 1.27 is 0.8980. Well, great. I labeled this negative E99. I didn't need to know that right now. I didn't need to know that to use the table, but I'm just giving it to you just to be concise. What does that mean? 0.8980 means that 89.80% of all the thermometers had a reading below 1.27 using the table. Okay, how can the calculator find this answer? I don't want to use a table, all right? I want the calculator to do it for me. Well, I go to second function bars, I come down to normal cumulative, the second one, not the PDF, the CDF, normal CDF. It requires 4 different numbers, all right? Here again, I've drawn my bell curve. I know this is the area that I'm looking for. It requires a lower limit. Lower means the small number. I'm going all the way out till I can't go any further. It's negative infinity. The calculator does not have a key for infinity. We use the negative sign followed by E99. What that means, ladies and gentlemen, it's a -1 followed by 99 zeros. That's infinity. Trust me. You get a 1 followed by a -1 followed by 99 zeros. That's a darn big negative number. For all intents and purposes, it's negative infinity. That's my lower limit. All right. My upper limit is 1.27. I'm finding the area from here all the way to there. What's my mean? It tells me it's 0. What's my standard deviation is 1. I press enter, I get the right answer, and I'll show you in a second. Now, if for some reason you've got an 84, which I know there's one person that does have an 84 that behaves like an 83, it's different. When you press normal cumulative density function, number 2, after you go to the second function vars, it just sits there looking at you. What you've got to do is put these 4 numbers in the same order. The lower one first, comma, the upper one, 1.27, comma, the mean, comma, and then the standard deviation. Once again, the lower followed by, just the way you see it here, the lower followed by the upper, the mean, and standard deviation. At least these are almost alphabetical. Lower comes, L becomes before L, and mean begins with the letter M, standard deviation begins with S, so M before S. I mean, all kind of ways you can think about it, or simply write it down. If that's the case, either you have an 83 or you got an 84 that behaves like an 83. I know there's one person. So a lot of these slides, I've actually shown how to do it with the 83 or the 84 that behaves like an 83. All right, so 0.898. If I had actually hit enter here, and the answer would have come out to be 0.8980. I didn't do it. Okay. All right, but the answer would have matched up real close. I think this one here would have been spot on. I just didn't do it. But whatever it is, you know, it's better than going to a table and doing it. All right, even if there's a little bit of discrepancy, I'll make sure that there's not 2 answers that are real close. All right, so that's when we were finding the area to the left. This one now says, hey, what's the probability that this thermometer reads above -1.23? Well, the first thing I would do is draw my curve. My highest value at the peak of this bell curve, right below is 0. It's the mean and it's also the median. They're synonymous. Well, if this is 0, ladies and gentlemen, negative numbers on a number line are to the left of 0. -1.23 is not going to be to the right of 0. It's going to be to the left of 0. You got to do some thinking here. If you're not drawing the curve and putting this in the right spot, you ain't got a shot of doing this. But what is he looking for? The area that's bigger than -1.23. I want this area to my right. The area that's associated with this value is from here to the left. To the left. It's a left-handed table. And there I am. I'm reading -1.2 and then 0.03 together is -1.23. I'm reading 0.1093. That's this little smidgen to the left. It can't be this big region because this big region is more than half. I mean, right here, if I draw a vertical line right here, from here to the end is half. How is that going to be 0.1093? No, it's the area that's associated with that z-score is the area to the left. You want the area on the other side. How do you find that? You use the complement rule. You take 1, you subtract 0.1093, and you get what you're looking for. You got to draw the bell curve. You got to label it properly. You got to know that negative numbers are to the left of 0, not to the right of 0. And also, don't fall for the trap. You go to a table and you read it. Not that you will, but that's not the area you're looking for. You're looking for the area on the other side of it. All right, I did it again, you know, -1.2. I'm just showing you how I got that answer of 0.1093. All well and good. The calculator will do this for us. All right, I've drawn my curve properly. I put this negative on where it belongs. It's my lower limit. All right. Even if I had filed this up, if I had put that on the right side, guess what? It still would be my lower limit. Lower limit's always to the left. It's a small number. Lower means smaller number. There it is, -1.23. I'm going to E99. All right. Second function, the comma key followed by a 99. What's my mean? 0. My standard deviation is 1. And there it is. Notice this answer was spot on to using the table. Here I've done it with an 83 calculator, which means I got to put all 4 numbers in separately, separated with a comma. Lower bound, upper bound, no big deal. Mean of 0, standard deviation of 1 saves you all the hassle of going to the table and doing any subtraction. Your calculator just does it for you, as long as you tell it the right lower and the right upper. Yeah, I don't know how you're going to figure out the right upper and the right lower and the right upper without drawing the curve. There's no way. You know what you're doing. You got to draw the curve and make sure you put 0 in the right spot here. The mean here is the highest point on the curve. All right, so we did a left to start out, then we did a right. And sometimes the hardest ones, if you are using tables, would be if you want to find the area in between, between -2 and 1.5. What's the probability that the freezing point of water was between -2 degrees centigrade and 1.50 degrees centigrade? Well, here's my 0. 1.5 is a positive number. It's to the right. Negative is a negative number. It's to the left. I'm looking for the area in between. If I was using my table, I would go to my table and find the area that's associated with 1.50. That's from this vertical line all the way to the left. Right here, he tells me it's 0.9332. I go to my table, I look up z-score of -0.2. It would tell me the area from here to the left is 0.0228. And then I take the bigger one, subtract the smaller one, and guess what? I would get what I needed, the area in between. Take some time. Without a calculator, that's what you would have to do. All right, that's what you have to do. And notice the answer came out to be 0.9140. Forget that. Let's use the calculator. All right. As long as I've drawn my curve properly, there's my -2, my lower bound. There's my upper bound, because I know what I'm looking for. All right. Once I draw my curve, I label this -2, I label this 1.5. I'm shading in this area in between. So I know that's my lower number. That's my smaller number, -2. My upper value is 1.50. These are standard normals. The mean is 0. The standard deviation is 1. What could be easier? All right. Here I do it with the 83. I'm not sure. Here again, I didn't press enter to find out how close the calculator gave me to 0.9140. In most cases, in section 6.2, they're going to be pretty close, pretty darn close. All right. And if you can't live with that, you can always use the table. Not many people do it, but if you're a stickler that you want to be precise, I don't think you have that much time. Here again, I will make sure that you don't find, I'm not going to give you an answer on your test that's 0.91404, 0.9105, and 0.9106. I'm not going to be picky like that. Be picayune. All right. Don't be, if the answer is not 0.9104 on your exam, it'll probably be 0.9103 or 0.9105. It'll be nothing else even close to it where you're not scratching your head. I mean, it's 40 problems. You haven't really got a lot of time to go and use the table, but some people will. Some people will. All right. Area to the left, area to the right, area in between. You get a lower bound, an upper bound. You got your mean and your standard deviation. It says, hey, sometimes though, we need to find the X or the Z score that's associated under a normal curve. We started out with finding areas, which were probabilities. We were given the X, and the X score suspiciously was the same as the Z score, all right? But sometimes he doesn't give us the X or the Z, he gives us the area. He's flipping the script. What we're going to be using is called inverse normal distribution. It's right below. We were using this, right now we were using normal CDF. We never used number 1. We were using this normal CDF. Now I'm going to be using what's called inverse norm. All right. He says to find a Z-score corresponding to a known probability, press second function var, select inverse norm. All right. Question here is find the score that equates to the 95th percentile. Folks, if you scored in the 95th percentile, you did darn good. You scored better than 95% of everybody else who took the test. All right. I'm looking for the Z-score that equates to this area. All right. Now I label this 5%. If this is 95%, you get 5% remaining. 5% doesn't play anything in the problem. I'm just drawing it to scale, so to speak. The 95th percentile, you're way out here. Your score was way here. 96th percentile, 98th percentile, 99th percentile would be way out here somewhere. The idea is that's your area. All right. Well, if I was using tables, now I got to go into the body of the table and find out what Z-score matches up with 0.9500, 0.9500. Well, this is one of the unusual ones. There is no 9500, but he tells, in fact, 9.9500 falls halfway between 9495 and 9505. He tells me that the z-score related to this is 0.1645. That doesn't happen often. A lot of times, you gotta search the table, and it's not like Price is Right, where it's closest to without going over. No, it's just simply closest to. It becomes a headache, especially you're taking a test and you're tired and you're trying to find values in this crazy old table. All right. But it can be done if you're using a table. That's what you would do. You find in the body of the table, then you equate. This is the one that I flat out gave us. Once again, the calculator comes to the rescue. When you're given the area and you need to know the z-score, you go to second function, bars, you come down to inverse norm. And inverse norm asks you for three things. It asks you for the area in question. Well, the area is 0.95. Mean hasn't changed, it's still 0. Standard deviation hasn't changed, it's still 1. Here's what it would look like on an 83. It doesn't prompt you like the 84 does. You have to remember, area goes first, mean goes second, separated with a comma, and standard deviation goes last. 1.645, what could be easier? Here we're looking for this z-score and that z-score. Notice this one's going to be negative and this one's going to be positive. We're finding the bottom 2.5% and the upper 2.5%. This is the bottom 2.5%. That's the upper. Now notice these guys express as decimals 0.025 and also 0.025. Somehow I gave you this answer right away, but the question is, let's assume that I went to my table and I looked up an area in the body of the table of 0.025 and the closest, and I found out that the z-score related to that was a negative 1.96. Well, guess what? This curve is symmetric. If this little smidgen is if this value here is negative 1.26, guess what? On the other side, it's going to be a positive 1.96. Another way of thinking about it is, if I take 1 and I subtract this little smidgen, the area from here all the way to the end is the difference here. If I went to the body of the table, guess what? It would give me a value of positive 1.96. All right, and there you see it there. All right, there you see it there. Show me how the TI can make it easier. Well, what I did was I went inverse norm. I gave it an area of 0.025. Mean was 0. Standard deviation was 1. It gave me a value of negative 1.96. Well, guess what? This is a negative 1.96 on the back end here because this curve is symmetric and these little areas are exactly the same. This is going to be a positive 1.96. If I didn't know that, if I wanted to find this score here, the area that's associated with that value right here is from here all the way back to the end. Well, if this little smidgen is 0.025, take 1, subtract this little smidgen, the remaining portion from here all the way back to the end is 0.9750. You pop that in for an area, mean of 0, standard deviation of 1, 1.96. But what I would tell people, if this problem were on a test, if I knew this answer, I also know that one. They just differ by sign. One is to the right of 0, positive, and the other one is to the left of 0, and it's negative. Standard normal. Go to your left, go to your right, go in between, and sometimes I flip the script. I don't want the area, which equates to probability. I'm looking for the X or the Z score. You used inverse norm. Inverse norm. All right, so that's section 6.2, standard normal. Well, 6.3 is non-standard normal. There's only one thing that is different. The mean is not going to be 0 and the standard deviation is not going to be 1. That's the only difference. You're still going to draw the curve. You're still going to figure out, am I going left, right? Am I going in the middle? The only difference is, instead of putting in 0 for the mean and 1 for the standard deviation, it's going to be some other values. All right, non-standard normal, which means the mean is not 0 and the standard deviation is not 1 or both. In most cases, it's both. Neither one holds true, not 0 and not 1. All right, so here again, we're going to, if we're doing it pencil and paper using the tables, we've got to standardize this. We got to take these X scores and change them to Z scores. Now, remember back in the standard normal, X and Z were synonymous. There's no change. All right, we took the X score, we subtracted the mean 0, divided by 1. X and Z were exactly the 1. Not the case here. All right, in a non-standard normal, you got to find the Z score if you're using a table. But the same things are going to apply. We're going to be finding area to the left, area to the right, and area in between. Nothing else changes other than the fact mean's not 0 and standard deviation is not 1. You get a water taxi. The mean of everybody on board is 172 pounds. Standard deviation is 29. I've highlighted these. If one man is randomly selected, what's the probability that that man weighs less than 174 pounds? Once again, I got to draw my curve. Here's my mean, the highest part of my graph. I put that in as 172. Why did that? I did that because I realized that 174 is bigger than 172. It's slightly to the right. How far to the right? It's immaterial. Less than 174. Well, here's 174 right here. Less than means the area to the left. Less than, smaller, less than. It's not going to be to the right because right would be greater than, less than. So you got to draw the table. What I'm looking for is this area. Well, doing it with the chart, I would have to take and convert this 174 to a Z score. The 172, the mean is going to become 0. 172 subtract 172 is 0 divided by whatever is going to be 0. I had to calculate, take 174, subtract the mean of 172 divided by 29 to figure this out to be 0.07, correct the two decimal places. Already I'm tired. All right. Now I'm going to look up 0.07 on my chart. 0.0 added with 0.07 is 0.5279. All right, there it is, 0.5279. But already, you know, I had to spend some time. I had to convert this X score to a Z score and then go to my table. All right, all well and good. But the calculator can do that for me. As long as I've drawn my curve properly, I'm looking for the probability that my X value is less than 174. Here's 174 right here. Less than means the area to the left. Well, how far to the left? As far as you can go is negative E99. That's my lower limit. There you go. Sometimes the calculator puts the 1 in for you. Remember, if you're using that negative sign, it's the gray key and not the white. It's the white key, not the gray key. It's the one at the bottom, not the one on the right. The upper limit, there's my lower, there's my upper, 174. Here is the only difference between standard and normal. In standard normal, the mean was 0. Guess what? The mean is 172. He tells me 172. Standard deviation is not 1. Standard deviation is 29. You're doing exactly what you did in section 6.2. It's just that the mean and standard deviation on 0 and on 1. Now, here's what I'm talking about. Notice doing it with a calculator, there's 4 10,000ths error, which isn't huge, all right, but there will be some error. Well, if you say to yourself, oh, I can't live with the fact that I didn't get the right answer, well, then do it pencil and paper. But here again, I'm not going to put more than one answer, you know, that's going to be close to the correct answer of, this is a spot on answer. Your calculator gave you this. This answer will be the only one that's close to the real answer. This one here is off by 4 10,000ths. All right, 4 10,000ths, which isn't very shattering. I won't put more than one answer. I wouldn't put 0.5277 and 0.5279. No, I won't do that to you. Even though you're off by 4 10,000ths, this will be the closest thing to what your calculator gives you. And the only way you're going to get this answer spot on, if you just went through everything I just went through here, you know, going to your table and all that stuff, that's the only way you're going to get spot on. It's not worth the, well, I should say it's not worth the effort. For some people, it may be worth it. All right, what if we wanted to find the area in between? Oh, watch what happens here. I'm going to have to change both of these to Z scores. I took 19.7. I changed it to a Z score. I took the score, I subtracted the mean, divided by the standard deviation, negative 0.96. I took this X score, I changed it to a Z score. Now I got to look up both of these, one on my positive Z score chart and this one on my negative Z score chart. Well, I did that. And these are the numbers I came up with. I came up with Yeah, I came up with 20, I looked up 1.38 on my chart, and I came up with an area of 0.9162. I looked up negative 0.96 on my z-score chart, my negative one. I came up with an area of 0.1685. And then finally I subtracted two and found out the area in between. Well, that would take me almost a good 7 or 8, maybe longer to do that. I gotta change these to z-scores, go to my table and do all that stuff. All right, there it is. That z-score gave me an area of that. And this z-score gave me an area that I subtracted to find the area that I'm looking for. But of course, my calculator comes to the rescue. If I'm looking for the area between 19.7 and 25.3, well, guess what? 19.7 is my lower bound. On my high end, my upper bound is 25.3. You know the mean to be 22, and you know the standard deviation to be 2.4. So there's no need. Now, what's interesting about this, the correct answer, notice what the calculator gave you, 0.7465, but the correct answer is 0.7477. You're saying to yourself, well, 0.7455 is closer to that. When we're in class, I've mentioned this over and over again, and I would sneak a problem like this in on people. All right, and they would fall for it. And I've been telling them, I would be saying, hey, listen, if you have two answers that are close, what the purpose of giving you a problem like this is to force a person to have to go to the table. I'm not going to do that because of the fact of what we're doing. We're doing this online and everything else. And, it's a 5-week course. But do you see what I'm saying here? So what would happen is if your answer was 0.7465, I would not have this answer. I'd have something crazy. Here's a crazy one. Probability is more than one. It can't be that. No, this one here, I'd make a number that's way, in other words, this would be, if your calculator gave you that, this would be the only number that was even relatively close to 0.7465. In fact, I would give you an answer of only one number that started out with a 0.7 and a 4. All the other answers, I would not give you something like this, not to confuse you. But you see there's quite a bit, well, I see quite a bit of discrepancy, there's 12 10,000s. All right, it seems like there's a lot of difference, but in actuality, there's not. But I would not give you something like this because the correct answer was not the one that was closest to what the calculator gave you, was this one that's furthest away. All right. And once again, like in section 6.2, sometimes you need to find the X score. You know the area, you got to find the X score that's associated with that area. Here's the one that says, hey, find what it says, find the weights that separates the lightest 95.5% from the heaviest. Well, the heaviest is to the right, the lightest is to the left. This is the value that separates the lowest 99.5% from the upper 0.5%. I'm looking for this value here to the left. Well, there's my mean, and well, I don't know my score yet, but I have to standardize this. I got to take this and standardize it. So I go to the body of my table. I would find the z-score associated with 0.9950. It's one of the ones they gave you, which is 2.575. Okay, great. All right, great. I know that the z-score is 0.2575, but I still need my x value. That's a z-score. I need to know my x value. Now I know if this number here is to the right of 172, this x value is going to be bigger than 172. I would have to take the formula. I would have to take the formula for z-scores, do a little bit of algebra, and say to myself, oh, if I know the z-score and the mean and the standard deviation, to find the x-score, take the mean, add it with the z-score times the standard deviation. I would have to do that. If I did it properly, here it is all done out for you, I would find that that x-score is 247. It kind of makes sense. If this is 172, yeah, this number here is to the right of it, it's going to be bigger, quite a bit bigger, 247. Wow, a lot of work. A lot of work. I got to go to the body of the table. Body of the table gives me a z-score. Now I got to take that z-score and I got to translate it to an x-score. All right. But my calculator comes to the rescue. All right. Inverse norm. What's the area? I'm looking for this x value here. What's the area that's associated with this x value? Is from here to the left. Oh, I know that. 0.9950, 99.5%. You gotta remember 99.5% as a decimal, move the 0.2 places to the left. All right, 2 places to the left is 0.9950. You put the wrong number in here, don't blame the calculator because you couldn't change a percentage to a decimal. A decimal to a percentage, you move the point 2 places to the right. Yeah, and then from a decimal to a percentage to a decimal, 2 places to the left. All right, so the area here was 0.9950. He told me the mean was 172. He told me the standard deviation was 29. I hit paste, 246.70. And if I round this up 246.7, it's pretty much spot on, rounded up to 247. So not bad. But look at the difference between what it takes to do the table versus using the calculator. But still, you gotta be precise. You gotta have the right area, obviously key in the right mean and key in the right standard deviation. All right, so 6.2 has both things, looking for the area, the probability, and then you flip the script and you find you use the inverse norm and you go at it. I've got 8:36, so I got pretty much 24 minutes to finish this off. You'll see it labeled. You'll see it when chapter 6 starts, you'll see it labeled standard normal. All right, and then when section 6.3 starts, you'll see it labeled non-standard normal. The difference being means not 0 and the standard deviation is not 1. When you get to section 6.5, it'll be labeled central limit theorem. Central limit theorem. All right, notice what he says here. He says, up to now, we've been finding probabilities of one individual of one item. He says, now we're going to work with multiple items. In this case here, he says, find a probability that 20 randomly selected men will have a mean weight greater than 175. What we're doing with a central limit theorem, we're not working with one item, one person or one item. We're working with the mean of multiple items. And I'll tell you straight out, when you see it labeled, hey, here, we're now entering the central limit problems, I've actually bolded out the fact that you're not dealing with one item or one person, you're dealing with multiple people. This is what's called your end value. All right. When we went from standard normal to non-standard normal, what was the change? Mean wasn't 0, standard deviation, it wasn't 1. When we move to the central limit theorem, mean's not going to be 0 again. Standard deviation is not going to be 1, but we've already dealt with that. The other thing that changes, the other little quirk here is that the values, the mean of multiple items decreases, makes smaller the standard deviation. So when it comes time to put the standard deviation into your calculator, you've got to put the original standard deviation divided by how many items, the square root, of how many items you're talking about. That's the difference between 6.5 and 6.3. All right, it's how you enter in the standard deviation. The mean stays exactly the same. The only thing that changes is the standard deviation. It becomes smaller. How do you make it smaller? You take the original one, you divide it by how many people, how many items you're talking about. All right, find a probability of that if I pick 20 randomly selected men, the average of their weights will be greater than 175. All right, so I drew my curve. Here's my mean of 172, the highest point. 175 is to the right. So I want probability of greater than. Well, greater than means to the right. All right, so now I got to change this 175 to a z-score. I got to change it to a z-score. So I take my x value, 175, I subtract the mean. Now I divide it by the standard deviation. Well, the standard deviation now is the original 129 divided by the square root of 20. I got to put this into a calculator, all to give me a z-score of 0.46. I go to my table, 0.46. Here it is. It's the area. The area works out to be 0.6772. But guess what? That's the area to the left, because the z-score, the area associated with this number, is to the left. I'm not looking for that. I'm looking for the other side. So I have to take this number and subtract it from 1. Already I'm tired. Let's let the calculator do everything. All right, I drew my curve. I want the probability that the mean of 20 men is greater than 175. Well, if this is 172, there's 175 greater than means area to the right. All right. So my lower limit is 175. I want from here all the way till I can't go any further, positive infinity. My low value is right here, 175. My upper value is E99. My mean is 172. Now the difference between 6.5 and 6.3 is now my standard deviation is not just 29, it's 29 divided by the square root of how many people I'm talking about here, 20 people. Do not figure this out on your own. Let the calculator do this. No, there's no need of taking 29 and dividing it by the square root of 20 on your calculator and come up with some crazy decimal. Let the calculator do all of the work for you. Do not do this on your own. The calculator is perfectly capable of taking 29 and dividing it by the square root of 20 for you. All right, there's my answer, 0.3218. I'm trying to figure out 0.3228. The calculator gave you 0.3218. Pretty darn close. There'll be no other answer that'll be that close to it. All right, if you get 0.3232, if you get 0.328, 0.3218, it'll be the closest thing to 0.3228. It won't be spot on. The only way it's going to be spot on, ladies and gentlemen, and the reason your calculator is giving you a little bit of an error is because of the fact of what it's doing with decimal points and rounding. I mean, this here is a crazy decimal, so it's actually, I shouldn't say it's giving you an error. It's actually more precise than pencil and paper is to a certain extent because it goes up to 9 decimal places. That's why it's giving you error. It's being more precise. All right. And once again, I can't stress enough, if you're not drawing the bell curve, I don't know how you're doing this. The amount of snowfall during a certain mountain range is normally distributed, mean 78, got it. Standard deviation of 16, got it. What's the probability that the mean snowfall of 64 years? Oh, I'm working with more than 1 year. Oh, guess what? Because I'm in what? I'm in central limit theorem. On the exam, I'll actually bold it out so it's like right there in front of you. You're working with more than one item. You're using the central limit theorem, which means that how you calculate the standard deviation changes. But hey, you don't need to know that because you're going to use your calculator. All right, I drew my curve. There was my mean. My high is 0.78. I'm looking for being exceeding 80.8. Exceeding means getting bigger. All right, this is my 80.8. This is 78, 80.8 to the right of it. Bigger than that is from here all the way to I can't go any further. There's my lower limit. There's my lower bound. There's my upper bound. All right, there it is, 80.8, my lower. There's my upper, E99. He told me the mean was 78 right here. What changes, ladies and gentlemen, is how you calculate the standard deviation. It's 16 divided by the square of 64. Here's a case where 64 is a perfect square. Hey, square of 64 is 8. Even I can figure out that 16 divided by 8 is 2. So here's one I could have done in my head. All right, I could have done it in my head because I know 64 is a perfect square. In either case, you press paste, and the answer came out to be 0.0808. Guess what? Spot on. All right, it's nice when they're spot on. It's not always going to happen, but there'll only be one answer close to what your calculator is giving to you if it's not spot on. All right, the weights of fish in a certain lake are normally distributed, means 13 pounds, standard deviation of 9. Okay, if 9 fish, not 1 fish, 9 fish are randomly selected, what's the probability that mean weight will be between 10.6 and 16.6? Well, there's my mean, 13, right? The highest point on my bell curve. 10.6 is to the left, 16.6 is to the right. There's my lower limit, there's my upper limit. All right, he told me the mean was 13. And once again, standard deviation is the original standard deviation divided by the square root of n. And is how many, in this case, how many fish? Well, hey, you know, square root of 9 is 3. 9 divided by 3 is 3. So save yourself some aggravation. Just, don't be afraid to take the square of 9 and divide it by 9. Divide it into 9. Your calculator can do it, but I'm sure you're capable of doing that. Clicking paste, and what do I get here? I get 0.6. Notice what's happening here, 0.6731. Look how darn close the correct answer is. There's nothing even close. There's nothing that even starts out with 0.6. That's 0.0, that's 0.3, that's 0.4. I mean, duh. That's what your calculator gives you. You're gonna pounce on that answer all day long. At least I would. And I should have given you one going the other way. I've given you two going to the right, but hey, it is what it is. Lower and up, it doesn't change. Bank loan officer rates applicants for credit, normally distributed mean of 200, standard deviation of 50. If 40 applicants, oh, more than one, central limit theorem. All right, drew my curve. My high point is 200. That's my mean. That's the high point on the graph, on the curve. Find a probability the mean is above 215. Well, if 200 is here, 215 is to the right of it. Above means from 215 all the way out to you can't go any further, E99. 215 is my lower, as you see right here. My upper is E99. My mean, he told me, was 200. How I calculate the standard deviation, because I'm working with multiple items, in this case 40, it's the original standard deviation of 50, which he told me here. The original standard deviation was 50, divided by the square root of n. N means, in this case, 40. How many different applicants? The calculator will handle that, no problem. I mean, it's a calculator for crying out loud. That's one thing to do, give you the right answer. 0.0289, and look at the correct answer, 0.0287. Nothing even, there's nothing even close that starts out with 0.0. So, you know, you get this answer, you know, oh, I think it's 0.1. No, come on, 0.0287. Your calculator gave you 0.289. If you don't want to do that, then you've got to do it pencil and paper, go to a chart, and to prove what to yourself, that you get the spot on answer. Yeah, you just waste about 15, 20 minutes. You can get that kind of time. I had you get this calculator for a reason. I had you get it for a reason. All right, I'm glad to see we got 2, 4, 5, 6, 7, 8, 10, 11, 13, 15, 17 people. Where's everybody else? You know, life gets in the way. I had a young lady, I had someone, I'm not going to mention any names, and the person's son got sick. All right, so obviously, when if you have kids, when your kids get sick, you take it pretty seriously. And long story short, you couldn't make it tonight. All right, but I do take attendance. I'm going to be perfectly blunt with you. You've made every one of these meetings, all right, because at the end of the course, what I normally do, because of the fact that it's, you know, we're still in the COVID situation to some degree, and, doing things remotely is not the same way as doing them in class. There's a lot of other things I would do if we were in class. Namely, I'd break you into groups and one person would be helping another. I mean, it's a whole different teaching strategy. All that being said is I usually boast of the grades, the final average, minimum of 3 points. But I'll be very front with you. I'm going to look at attendance. If you've made every meeting, whatever, and I can tell that you spent the time and you just didn't try to rip me off, chances are you receive more points. People that are trying to okey doke me, I can't control what goes on here. I can barely control what goes on in my life. All I know is that if you've been consistent and you've logged on every time, you will be quote unquote rewarded. So sometimes the average that you get, that's Canvas, is not the actual average. I don't deduct points from anybody's score. I don't deduct points, but that doesn't mean that everybody's going to receive the same amount of extra points. And you'll never know what I gave somebody else because they won't tell you and they won't even know themselves. But you will be rewarded because you had the due diligence, you had the presence of mind, you had the steadfastness to log on and listen to me ramble for 2 hours. So listen, if you're planning to log on to the office hour Friday, please have questions, but don't be telling me, oh, give me a minute while I find. No, have it ready, be organized. Nothing drives me up a wall. I try my best to be organized and have this stuff done. Please follow through, be organized. Don't waste your time, and sure as heck, don't waste my time. If that sounds kind of harsh, I'm sorry. Be ready for me on Friday. And I don't want to hear, well, I'm just in that. No, we all have excuses. Be ready. Let's make a good time, best use of our hour together. Second thing I want to remind you of, by Friday, probably, all right, you have one more assignment to do. That has to do with sections 7.1 and 7.2. Actually, you start 7.1 tonight. I'm going to post the last assignment, which is scheduled for Monday, and the date of Monday is the 9th. I'm going to post that last homework assignment probably Saturday, so you have a head start on it. And then what we'll do, rather than having a Zoom meeting next Wednesday, which we can't because next Wednesday the test starts, we will do the Zoom meeting the night before the Tuesday. And I know, you're saying, well, Mr. Gomes, it's said on Canvas, it's said on the website, Master Sorry, the class was on Wednesday. If you can't make it, I always record this stuff. All right, I always record it, so make sure you watch the recording. I still will take attendance. Because I always do that, but yeah, we've come down to, there's 2 more meetings that I'll actually be with you. I'll be with you Friday for those that can join the office hour, and next Tuesday, but I will remind you, I'll be reminding you probably 2 or 3 times. If nothing else, I do stay in contact with you folks, all right? And then next Tuesday, we'll do 6, 6, 7, 1, and 7, 2. And then I'll try to go back and answer any questions that are lingering. I just want you to do well, because this one is a little longer as far as time wise. There's more questions. It's 40 questions versus 35. Right about now, I'm exhausted and I'm going to sign off. You guys have a great weekend. Listen, you are so close to finishing this. You don't want to blow your average by not doing the work it's going to take. You got one more push to go through. You got Wednesday, Thursday, Friday, Saturday, Sunday, Monday, Tuesday, and you're done. You've completed this. Do not blow your average because you got lazy over the last few days. We're in the final stretch. We're in the 4th quarter for those who've played sports. You're in the final 4th quarter of the game. You want to finish up strong. Don't blow it now. I'm always available to answer questions via email. All right, that being said, have a great night. And thanks for letting me ramble for
Thank you. Have a good night.
an hour,
Thank
2
you.
hours.
Thank you.
Have a good
Okay,
night.
no problem.